Oh, uh-oh. Okay, there we go.
There we go. Okay. So what are you trying to do with it, Cheyenne?
I'm trying to divide it into 256 by 3, but you said you'll do it as a fraction, so I'll put,
Well, you didn't just divide 256 by 3. Didn't you do some kind of root with it?
yeah, I did a 4th root.
The fourth root with it, right? Why would it make sense to deal with a fourth root in this case?
Because it's 4 common ratios.
4 common ratios to get to this 256 divided by 3, right? So a fourth root would make a lot of sense here. But Zay, what did you include within this that Cheyenne is forgetting? So Cheyenne just did a fourth root of 256 divided by 3.
You talking about that little R stuff I did?
Kind of, that's part of it, but what did you do to the 256 divided by 3 before you...
I divided it by 27.
Remember how you said it was a common ratio, right? Did you actually do a ratio of the current value to the previous value? That's what you might be forgetting about. Does that make sense? Then you might be able to do a fourth root.
So I did 256 divided by 3 divided by 27.
You can do it that way, right? You would want to group these together. What I showed Zay a second ago, and you might want to remember as well, is that technically that 27 is divided by 1, and how do you divide by a fraction?
It's reciprocal.
You multiply by its reciprocal. So that would be the fourth root of 256 divided by 81. That's a little bit easier to work with. Plug the fourth root of 256 divided by 81 in your calculator.
Crap, wrong one. 64.
The fourth root of 256? That's the square root of 256 times 4.
4 over 30.
Remember, and I would just use the calculator I have, but so you can
Oh,
do
that's
that.
what I got.
Now you can do a fourth root. See how it's in the little crook? And you want 256 divided by 81. So you get a
4.
common ratio of 4/3. Which is what I did to get to that 256 over 3. Because if I do 27 divided by 3, I get 9. 9 times 4 is 36. 36 divided by 3 is 12. 12 times 4 is 48. And then 48 divided by 3 is 16. 16 times 4 is 64. Multiply by 4/3 again, you get 256 divided by 3. I will point this out though. This is not my favorite strategy. It works. But there's a different strategy that will work better for you today on today's task if you do it this way. Linnea, how did you approach this problem?
I tried to do, like I counted how many. So I put 3 times r to the 4th equals 256 over 3.
So 3 times r to the 4th
Mm-hmm.
is equal to 256 divided by 3.
Mm-hmm.
Why'd you put a 3 here?
Because I counted how many were missing, and there's 3 to get to 256 over 3.
I got you. However, so I'm more like this part of it, right? Because the idea is not just how many you're missing, it's more about multiplying by that common ratio. So how many times did we multiply by r?
4.
4 times. And how do we show repeated multiplication? With an exponent. R to the 4th, I love it. But what did you start with? What did you multiply by r to the 4th? You didn't start with 3.
27.
You started with 27, didn't you? Notice I'm starting at 27, then I'm repeatedly multiplying by r 4 times, and at the end of all that it's 256 divided by 3. Now you could divide both sides by 27, but this is why, again, I love a reciprocal. I already have a fraction on the other side, so I'm going to multiply by 1 divided by 27. This will speed things up, because what is 27 divided by 27?
1.
1. I'm creating that 1 right here. 1 times r to the 4th.
R to the 4th.
And then 256 times 1,
256.
3 times 27.
That's a tough one.
But you have calculators for that. Then what are you going to do to solve for r at this point?
Divide.
Not divide,
4 3.
not 4 over 3. What are you going to do to solve for r? What did you say?
4 3.
Oh, 4 3. I thought you said 4 divided by 3. I was like, no. Notice, I've got r to the 4th, so I'm going to do a 4th root. R is equal to
R.
4 thirds.
So each time you multiply by 4/3.
Yeah, isn't that what we just said here, that our common ratio is 4 thirds? And that's what I showed, is I was repeatedly multiplying by 4 thirds to get each of these numbers. And that's what this equation is really saying. I like approaching it this way. You can do it the other way. But notice, what am I starting at? 27. Then what am I doing to it? I'm multiplying by r, and r, that common ratio each time. So I multiply by my common ratio 4 times. And at the end of all of that, I got to 256 divided by 3. Now I just solved this equation. That r, that common ratio, is 4 thirds. Does that make sense? Yes, sir.
Do you have to leave it as a fraction?
No, but I would recommend it.
Okay.
Because here's the thing. Off the top of your head, do you know what 27 times 1.3 repeating is?
87 something.
Nope. It's 36.
Oh, yeah.
I don't know that off the top of my head, though. You could use a calculator, but it's pretty hard to put 1.3 repeating into the calculator, isn't it? Like, you can put 1.3333, but eventually you're going to run out of spaces. You can't put infinitely many 3's into the calculator. But what you can do is you can put 4 divided by 3 into the calculator. You can also do that in your head pretty easily, because that's really 27 divided by 3. What is 27 divided by 3?
9.
What's 9 times 4?
36. Oh, wow.
It is so much easier to work with a fraction because you can do the division first. And also, if it's a repeating decimal, you can't put the repeating decimal into your calculator, but you can put that fraction into your calculator. So I always leave mine as fractions.
I did a decimal, got the same thing.
Like you did the 1.3 repeating.
So I just ended up being, I never typed anything.
Let me see what you did. Oh, if you type that in though, it won't get you each number correctly. Like it'll get close, but if you do 27 times 1.3, you get 35.1. That is definitely not 36. You can multiply by 1.3 again. Right, you never get that 85, you're pretty far off. Because you're rounding too much, which is why I do a fraction instead of that decimal there, okay? So fractions are your best friends because they are much more accurate and much easier to work with. Okay, so we're going to wrap up a couple of things with 2.3, linear, exponential, or neither, and then do a quick exponents review for your homework tonight before we get started with 2.4 today. So, I need you paying attention. Number 11 here. 11, linear, exponential, or neither? I need you on 2.3. Exponential? Why? Anyone have justification for why this might be exponential?
Maybe the graph shows a curve, and then I wrote in
Table.
Okay, so this graph does show a curve, but is a curve always exponential?
the table,
No? You made a table though? What did you see in the table?
multiplying by 2.
It was repeatedly multiplying by 2. Notice, it's not just that it's exponential. If you look at a table for this, 0, 1, 1, 2, 2, 4, 4, 8. That is repeatedly multiplying by 2. You can go backwards, negative 1, 1/2, negative 2, 1/4. And so here's also an equation, right? Notice based off of this table, I wrote the equation 1 times 2 raised to the x. Now I want you to notice this. That means, well, first off, what we call a multiplicative rate of change a common ratio, but I also want you to remember that, because this came up on your understanding check and a lot of us missed this, right? Something that we multiply by, what is that called? So I took number 6 and I broke it down into its what?
No.
What are the things that multiply to give me 6? Factors, right? If we have equal factors, that common ratio, that's an exponential function. We have repeated factors there, and we want to pay attention to that. And also, when I look at the algebraic representation, what is in the exponent that makes it exponential and not a quadratic or something like that? But the variable is in the exponent, right? It's not just that we have an exponent, it's that the variable is in the exponent. Okay, please keep your mask up over your nose. Caroline, same deal. Alright, now I will point this out. You need to take notes on these different features, but this will be also on Schoology if you want to look at more detail and ask more questions. I did not mean to already have this one ready to go, but there it is. The time it takes you to get to work as a function of the speed at which you drive. So what I did is, first off, do they give you exact values here? No, they just give you this generic word problem. And so I honestly wasn't sure. I had to make something up. So what I did is I made this example of, okay, let's say you have to drive 20 miles to work. Well, if you're driving 5 miles an hour, it's going to take you 4 hours, which I hope no one's driving 5 miles an hour, right? But I just made this example. If you're driving 10 miles an hour, it's going to take you 10 hours to get there. 15 miles an hour, it's going to take you 4/3. 20 miles an hour, it's going to take you 1 hour. 25 miles an hour, it's going to take you 4/5 of an hour. So when I graph it here, that kind of looks exponential to me, doesn't it to you?
Mm-hmm.
But am I multiplying by the same thing every time? No.
So exponential is multiplying, linear is addition. Okay.
So, yeah, linear has that additive rate of change, where you have a common difference over equal intervals. A geometric or exponential has that multiplicative rate of change, meaning it has that common factor, that common ratio over equal intervals, right? And so, times 1/2, but that's not times 1/2, even though it's the same 5 minutes. Does that make sense?
Mm-hmm.
So it's a little bit different of a relationship that we look at later, so that's why it's neither. Alright, so number 13, 7x squared. I thought I made all of these so they would show up later, but apparently I forgot to do that. Notice it does have an exponent on it, doesn't it?
Mm-hmm.
So is it exponential though?
No.
No, why not? Hey Gavin, head up so that you can keep the mask all the way on. Thank you, sir. I graphed it wrong, what do you mean?
Well, I mean, they don't show an exponential graph.
Okay, so notice it does not show an exponential graph. Now where did I get this graph from though?
Something to do with
The calculator.
Not from the calculator. I used my brain for this one. I used a table, to be honest. First off, I know what this looks like because I've dealt with this math a lot. But if you're ever in doubt, can't you just make a table and plug stuff in for into the equation? Like -2. What is -2 squared? -2 squared.
-4. 4.
So it's a positive 4, right? What's 7 times 4?
28.
That's 28. What's -1 squared?
1.
1. 7 times 1.
7.
7.
What's 0 squared?
0.
7 times 0.
0.
Notice that's how I got my points there. Then 1 squared times 7, and 2 squared times 7. And when I look at the graph, does that look like an exponential curve at all?
Why
No.
do you start off at -2?
1, because of experience. 2, because in general, I like to start at 0, and then I go a little bit to the left and I go a little bit to the right. So it's not about actually starting at -2, it's more starting about that at that y-intercept, right? So starting at the input of 0 and then going around it. Does that make sense? So that's kind of where that came from. But the big thing I want you to notice is just having an exponent, does that make it exponential? No. The exponent needs to be a what to be exponential?
A variable.
The exponent needs to be a variable, right? That's what we looked at right here. The exponent needs to be a variable because that tells me that I'm repeatedly multiplying by 2. Okay? Alright, so each point on the graph is exactly 1/3 of the previous point. If I see a fraction of, what is that telling me to repeatedly do? Multiply. If I'm repeatedly multiplying, what is that?
Multiplication.
Exponent.
Actually, repeated multiplication would not be multiplication.
Addition.
No, repeated addition would be multiplication. Repeated multiplication is an
No, exponent.
exponent. Notice, where's the variable located?
Beside.
Not beside it, in the exponent. It's called an exponential because the variable is in the exponent. Right? Because I'm repeatedly multiplying by 1/3. But do I know how many times I'm multiplying by 1/3? No, that's why the exponent is a variable. We need to recognize again with exponential that it's those equal factors over equal intervals, which is where it gets a little bit interesting with number 15. Notice how I plugged in my 3. By the way, what type of equation are we looking at in 15?
Long division.
Don't think it's long division. What type of equation would this be? The current value is based on what values? The previous. What type of equation is it?
No.
That's a type of function or sequence. What type of equation is where the current value is based on the previous values?
Recursive.
Recursive, right? The current is based on 1 before and 2 before. So notice I plugged in my 3. 1 before 3 is 2. 2 before 3 is 1. And f of 2 is 7. F of 1 was 7. So 7 plus 7 is 14. F of 4 is based on f of 3 and f of 2. 14 plus 7 is 21. Is there a common ratio or a common difference in here? No. Plus 0, plus 7, plus 7. But those are not the same differences. Times 1 times 2 times not either of those. So again, not a common ratio. So that was why it'd be neither. Okay, notice how I'm looking at multiple representations to make sense out of this. Again, what type of equation is number 16? Recursive. What am I repeatedly doing to the previous value? Multiplying by. So remember, f of n minus 1, that's the output. That's the previous output. What am I doing to f of n minus 1?
Oh, multiplying it by 2.
Right. So I started at 1, 1, and then I repeatedly multiplied by 2/3. Y'all still giggling about how he said long division?
It's just
It's just her. Okay. So I had to get through that quickly so we could get to today's lesson so we could wrap it up tomorrow because this is important for when we get back from Thanksgiving break. Well, first off, I need you to understand this. Linear, exponential, and neither. Those are critical ideas that will show up on more understanding checks and they will show up on more tests. I've recorded this so that you can watch this video later. I have the slides up on Schoology so you can see these later. There's a certain point where you are responsible for making sure that you get the information you need. Sound good? I don't know yet. I was talking about for what's happening after the break with Christmas or before the 9 weeks exam. Alright, so here's a quick little review about exponent rules. Because I can go ahead and tell you right now, numbers 15 and 16 will be a part of your homework tonight. When you multiply numbers with the same base, like 7 to the third and 7 squared, by the way, this is in 2.4, at the very end of it, if you want to go ahead and take some notes there. Okay, so the very back of 2.4. If you are multiplying numbers with the same base, like 7 to the third times 7 to the second, what would you do? McKay and Caroline. Caroline. What would we do to multiply 7 to the third times 7 to the second?
7 times 7 3 times.
Well, so
Well,
7 to the...
times is still
Would
3
you
times.
flip it?
Okay, so that is a good way to
But
start.
Simplify.
So that's 7 times 7 3 times. What's 7 to the second then?
49. But
So here's the thing though, honestly don't want to do this 49 because that's going to... So what?
7 times 7.
Nah, yeah, I'm going to leave it at 7 times 7. How could I simplify this idea, right? I don't want to multiply it all the way out because that's going to be a huge number.
Wait, did you make your own problem or are you doing?
Yes, I made my own problem to help you with this one right here.
Oh.
So how could I rewrite 7 times 7 times 7 times 7 times 7?
7 to the
7 to the fifth. So I want you to notice right here, what can you do when you multiply numbers with the same base?
You
can make
you add
exponents.
the exponent.
You can add the exponents. This actually explains exactly why you would do that. What I'm doing is repeatedly multiplying 3 7s, multiplying 2 7s. So how many 7s are being multiplied? 5 of them. So if I have a to the third times a to the second, that would be a to the... Notice that's 3 plus 2. You're adding those exponents. And it's all from understanding that I'm repeatedly multiplying 3 a's times 2 more a's being multiplied, so it's 5 a's being multiplied.
What's number 18 about?
That's just 17.
We're going to talk about it later. Don't worry about it right now.
Oh, okay.
Okay?
It scared me.
It's not bad at all. Okay? When I look here at number 16, when multiplying numbers with the same base, I add the exponents. When I divide numbers with the same base, what am I going to do?
Multiply next time.
Subtract them.
What was the inverse of multiplication? Division. What's the inverse of addition?
Subtraction.
Subtraction would make sense, right? But let's start with what Zay just said. Remember how Zay said, okay, let's rewrite 7 to the third as 7 times 7 times 7, right? So 7 to the fourth would be 7 times,
7 times 7 times 7.
okay? Divided by,
7 times 7.
what is 7 divided by 7?
1.
What's 7 divided by 7?
1.
So it's 7 to the second.
So what did you do with those exponents?
You subtracted
You subtracted the exponents.
Oh,
Wait,
okay.
how you
Does that make sense?
How'd you end up with
Oh.
7 to the second? So notice it was 7 to the fourth, right? So 7 times 7 times 7 times 7.
You're just
And then we're dividing by how many 7s?
2 of them.
2?
2 of them.
And what is 7 divided by 7? 1. What is this 7 divided by this 7? So 1 times 1 times 7 times 7. That's only 7 squared. And so the really important idea here is if we're dividing numbers with the same base, what do we do with their exponents?
Multiply. Add, divide. Subtract them.
Subtract their exponents. So if you aren't aware of this and don't remember this rule, I would probably write this fact
I
down.
was making that up.
What am I supposed to write down?
Made it up to it's the same.
If you were multiplying numbers with the same base, what did you do?
I got it.
You added exponents. If you're dividing numbers with the same base, what are you doing with your exponents?
Hey, so
Subtract.
for number 16, you're going to take 2
Can you
from
repeat that?
3.
What you
So
just
they're
said?
going to be 1, so it's
What
5
did you
times
just
1
say?
is 5.
Okay.
Multiplying.
I mean, if that's what you want to put, but I'm not telling you the answer for the
Add
homework.
them.
I'm giving you the background you need to be able to do it on your own.
No. Alright.
So this would be a to the 4 minus 2, or a to the second. Notice if you are multiplying numbers with the same base, you add the exponents. That's something I would write down. If you're dividing numbers with the same base, you're going to subtract those exponents.
I missed up numbers.
Okay?
And what's
Say, I
the
need
one
you to
for
keep your-
adding them?
Mask up. Say again?
And what's the one for adding them? So dividing equals subtract. What's the other one?
Well, you need to be more careful with it. Dividing numbers with the same base. Subtract what?
Exponents.
Exponents. Multiplying numbers with the same base, right? You need to be very careful about that language. Multiplying numbers with the same base, you're going to add what?
Exponents.
Right. You need to be careful about that language. If you are not careful about your language, it will mess you up. Okay, so we're getting started with 2.4 at this point, which we might have to do the majority of this starting together. Okay, Moni, can you read our first objective for us today?
Okay. I can identify common factor necessary to find the output from an exponential function, even when input for fractional.
So we've mostly focused, even on geometric means, when it was integer inputs, right? Now we're going to start thinking about those fractional inputs. It's going to help us understand roots and rational exponents more. So we need to identify common factors even for this. This is why we did that warm-up with the geometric means. Caroline, can you read the second objective for us?
I can connect radicals, is that how you say it?
Mhm.
To rational exponents.
And so this is part of why we're doing that exponent information that we just did, because we're going to try to connect the idea of radicals to rational exponents to see how they go together. Alright, so number one, complete the following table. X and f of x, right? So x is 0, 1, 2, 3, 4. F of x is equal to 4 times 2 raised to the x. So if I want f of 1, what am I going to do for that?
Multiply.
Multiply what? And what did this 1 just take the place of?
X.
So it's going to take the place of x?
You multiply by x.
You multiply 1 times x?
We don't know one, two.
What is the equation, guys? F of x equals what?
4
4 times.
Oh, I got it now.
So wherever that x is, what's taking the place of it?
The one.
The 1. Now before we multiply this out, I want points on the out to you here. The y-intercept is what?
0. 4.
4. Notice that 4 is right here, where we're starting at. What are we repeatedly doing to that 4? Multiplying by 2. Notice how we have a variable exponent above the 2, so I know I'm multiplying by 2. So what should the next number be?
8.
4 times 2 to the first?
8.
8. So what's f of 2 going to be?
16.
F of 3?
32.
2.
F of 4? Okay? So we should see this idea of repeatedly multiplying by 2. And again, you can check it by plugging your 3 in. That'd be 4 times 8. 4 times 8 is 32. Any questions about that?
Makes sense.
Okay. Just hoping that that would be pretty comfortable to start us out. Sadie, you have this written down on the front of the task? Now, at this point, it does direct you to, on number 2, to plot these points on the graph at the end of this task and sketch the graph of f of x. So here is, on the very last page, you should see a pretty large graph there. I need you to graph those points.
Oh, there it is.
Yep,
Good enough.
pretty large graph at the back of the task. Nope, not there, Gavin.
Alright,
So just to clarify, let's see this real quick. It's before the ready set, it's in the middle of the packet. I should have said that, I guess. This is where we're looking. Yes. X, Y.
How do you
Huh?
How do you work?
Well, what comes first, X or Y? The way, and so like 1, I've just done it long enough that I know here's X. I mean, in the alphabet, what comes first? X or Y.
Oh, A.
And so the way that I was first taught it, and it's just stuck because I've done it for long enough, you gotta learn how to crawl before you can learn how to walk. So you crawl along here, but then you can stand up and you can walk.
I came off running.
Your mouth maybe, but mask up over your nose.
I was a third grade.
So please make sure you have those points on there accurately.
64.
Say again.
Is it continuous?
Which ones are we graphing specifically?
These points.
Okay.
0, 4, 1, 8, 2, 16, 3, 32, 4, 64. And McKay asked a very good question here. Is it going to be continuous? Does anyone know the answer to this?
Hold
Yes.
up,
No.
hold up.
Yes.
Why do you think yes, Cheyenne?
Because it can keep going up there.
So this is an important distinction. Continuous does not mean it continues forever. Continuous means that it continues between the points. Notice how the points are isolated right now. There's nothing around them. Continuous means that you're getting everything in between there. So should we be able to get everything in between there?
No.
Typically, when we're dealing with x and f of x, it is continuous. If we're dealing with n and f of n, it would be discrete, because n is usually what we deal with sequences, again, because it deals with, or it's the idea of the natural number set. So x is continuous, n is the natural number set. So typically, anytime you see x and f of x, it's a continuous function. Oops, I don't have it in there. But yes, I would...
But 4 times 2 would never equal 7.
Actually, that's what today is all about.
I should have come on that first.
Because here's the thing. If you're dealing with your integer values, you're 100% right, and we can never get 7. But remember how in the objectives it talked about those fractional inputs? If I plug in something in between 0 and 1, I would be able to get something that's a 7. Does that make sense? So that's what we're going to start looking at today, okay? So anytime we're dealing with x and f of x, what type of function is there? What type of model would it be? Continuous or discrete?
Continuous.
It's going to be continuous for x and f of x. And if you need to make that note to yourself, seeing as I've made that note or said that out loud multiple times, that'd be a great thing to write down. If it's x and f of x, it's continuous. It's a good thing to note to yourself.
N and what else is?
Discrete.
N and f of n, those are sequences and those are discrete. X and f of x, those are continuous. And for continuous functions. So, this is the next part of it, going back to the front of the task. Let's say we want to create a table with more entries, maybe with a point halfway between each of the points in the table above. There are a couple of ways that we might think about it. We'll begin by letting our friend Travis explain his method. Travis makes the following claim. If the function doubles each time x goes up by 1, then half that growth occurs between 0 and 1/2, and the other half occurs between 1/2 and 1. So for example, we can find the output at x equals 1/2 by finding the average of the outputs at x equals 0 and 1.
I bet it's continuous.
Say again?
I bet it's continuous.
Well, this is part of the idea of continuous, right? See how we're getting stuff in between now? But the idea is how are we going to get that? Because we already know... What am I trying to... No, that's not what I want. So we already know what's in between, or at 0 and 1 and 2, 3 and 4. What are those values? If I plug a 1 in, what am I getting out?
8,
8. Plug in a 2.
16,
3.
32.
And
64.
64. So the idea that Travis uses is that in order to get the stuff in between, we're going to do what to those numbers?
Divide.
Divide.
Is that what he says? Divide?
Multiply.
Does he say multiply?
What does
There's
it say?
something.
He says something. Read it.
Where's it at?
Function double each one goes up by 1, then
Multiply half. Multiply by half.
finding the average.
Thank you for reading all the way through the end. Finding the average. What's the average of 4 and 8?
6, 4,
How do you go
7.
B6.
B6. You add them together. Divide by the two numbers you added together.
I said 6.
That's an average, right?
You didn't justify that.
Now, what would be the average between 8 and 16?
12.
So 8 plus 16 divided by 2. 24 divided by 2 is 12.
And almost like I was right.
What about between 16 and 32?
24.
24.
I'm automatic, man.
What about 32 and 64?
48. How do you do that?
6,
I don't know, I
okay.
can't do math, but
16
I'm
plus
clicking right
8
now.
equals 24, and then you divide it by 2, and then you get 12. That's the average.
You can.
Why are you adding 8? Because that's what you're
Clicking,
doing.
Mr. Finn.
So, what do you think about Travis's strategy? Do you think that this is a correct way to approach these problems?
No.
Why not?
Seems excessive.
It's not that it's excessive. Say again.
It seems too easy.
It might be too easy. Well, here, let me point this out to you. What's the distance between 4 and 6?
2.
Distance between 6 and 8?
4. Wait, 2.
2.
What's the distance between 8 and 12?
4.
12 and 16?
4.
16 and 24?
8.
And then 8.
So
And
it
then-
doesn't have a constant.
Well, partially, but that's not the only issue. What type of function is 4 times 2 to the x? Yep. It's got a variable in the exponent, right? So it's exponential. And we just talked about the fact that an exponential function has a common ratio, which in the objectives, I had an F word in there, a common factor.
Say that word.
Are these factors? No. What type of function would have an additive rate of change? So notice it's not the same all the way through, but we're adding here and adding here, right? The same? That would be a what type of function? Linear. So Travis's idea of finding an average, which we talked about this before, and I want you to pay attention to this, an average, that is the same as an arithmetic mean. An average would work if it was a linear function, but is this linear? No. So do we want an arithmetic mean here? What do we want instead? Say it louder.
Geometric.
A geometric mean. We need to recognize that if it's an exponential function, we don't want an arithmetic mean, we want a geometric mean. Alright, so I want you to notice, alright, so you can see this graph here. Notice if you look here, you see how if I do this, it creates a linear piece right here, and then it's linear here, and linear here, and here. And it kind of creates a curve, but do I want linear pieces or do I want a smooth curve? Smooth curve. So commenting on Travis's idea, how does it compare to the table generated in problem number 1? For what kind of function would this reasoning work? Averages or arithmetic means would work for what? What would averages or arithmetic means work for?
Linear functions.
Would work for linear functions.
Set up the rail.
But this is what type of function? Not, it's a geometric sequence, so it's an exponential function. There you go. So, coming back to what you were just saying about, Cheyenne, we're going to have to talk about geometric means tomorrow. Alright, so that's what we're going to pick up with Miriam's ideas. So, notice we want to be able to identify common factors. That's what we'll pick up tomorrow. Here's your homework tonight. 2.4 ready, numbers 1 and 2. 6 and 7, set number 12, go numbers 15 through 16. I know it looks like a lot. Every single one of them is very quick, so I need you to make sure you're doing this homework. Tomorrow we will continue the in-betweeners. Have a good evening, or rest of your afternoon and evening.
Here, send that to me.
Is everyone taking a picture of what they need? Okay. What's up, James?
The big old book of stuff here today.
See ya.
So basically.
One second. I think this is still recording.